Okay, let's unpack this. You've got like a massive pile of stuff. Think photos on your phone, maybe your entire music library, years of documents.
Right. A huge amount.
Now, say you're looking for something like a specific item, finding that exact match. Well, it can grind things to a halt, can't it?
Oh, absolutely.
Yeah.
Especially when each item has tons of different characteristics, dimensions, as we call
The
it.
dimensions, right?
And what's fascinating here is that while finding the absolute closest item sounds ideal, um, it gets incredibly inefficient as you add more dimension.
It's like that needle in a haystack problem, but way worse.
Yeah, imagine trying to find a specific grain of sand, not just on a beach, but a beach that stretches across continents. That's kind of the challenge.
Exactly. And that's where our deep dive today takes us into the world of Approximate Nearest Neighbor Search, or ANNS. Forget finding the perfect twin. ANNS is about finding the one that's, close enough.
And the real magic is it does it lightning fast, or at least much, much faster.
Much faster, yeah.
Precisely. Instead of painstakingly comparing your search query against every single piece of data you have, ANNS algorithms use clever shortcuts.
Shortcuts.
Yeah, to zoom in on a much smaller, more manageable group of likely candidates.
And this isn't some, dusty corner of computer science, is it?
Not at all. This ability to quickly find similar things powers so much of our modern world.
Like what?
Well, think about databases surfacing related information, machine learning models making smart guesses,
Okay.
and even how your favorite music app suggests your next favorite song. Spotify got a specific shout out in the research we looked at.
Ah, Spotify.
Yeah.
And image recognition, too. Computer vision stuff.
Definitely. It's the engine behind a lot of that. If we connect this to the bigger picture, a fast, reliable way to do ANNS is just crucial.
It really underpins a vast ecosystem of technologies handling these enormous complex data sets. So our mission today is to get a solid understanding of the current state of these ANNS algorithms. We want to know what makes them tick, and figure out which ones might be the best tool for different jobs.
And we're not just guessing here.
No, we're diving headfirst into a really comprehensive research study. It pitted, 19 different cutting-edge methods against each other?
19, yeah. And this raises a key question for anyone dealing with large data sets. With so many algorithms out there, often developed in different bubbles like research communities or industry folks.
Right.
How do you even begin to choose? This study is incredibly valuable because it bridges those gaps.
So it looks at techniques from machine learning, multimedia, databases.
And even practical applications, yeah. It compares algorithms that hadn't really been put head-to-head before, like rank cover tree, product quantization, SRS, K-graph.
And what's really impressive is the scale of their comparison, not just a couple of data sets.
No, they used 20 different data sets.
Yeah.
Massive undertaking.
20. And they looked at performance in all sorts of ways. Search speed, accuracy, memory usage, scalability.
Right, robustness, too. It wasn't just about speed. Plus, the study tackled a persistent problem in this field: inconsistent results.
Ah, where different studies show the same algorithm doing wildly different things.
Exactly. Like, one paper says AGH is better than spectral hashing, another says the opposite. So this study aimed for a fairer, more consistent comparison, a level playing field.
Okay, so we know why this matters. We've got this great study as our guide. Let's get into the algorithms themselves. The study groups them into 3 main buckets, right? Hashing, partitioning, and graph-based.
That's right. This categorization helps us understand the fundamental strategy each type uses. Let's start with hashing-based methods.
So hashing, not like passwords and security, right? A different kind of hashing.
Totally different, yeah. Not cybersecurity. Here, the core idea is mapping those complex, high-dimensional data points down to much shorter hash codes.
Like a simplified ID tag.
Kind of, yeah. Think of it like giving each item a fingerprint. The goal is, if 2 items are similar, their short codes will also be similar, or maybe even the same.
Which makes comparisons super fast.
Exactly. And within hashing, the study highlights 2 main subcategories: locality-sensitive hashing, LSH, and learning to hash, L2H.
L2H, okay, what's LSH?
Locality-sensitive hashing, or LSH, is data independent, meaning it doesn't look at the data itself to decide how to create these codes. It uses pre-designed hash functions where similar items just have a higher probability of getting the same code. They collide.
So the rules are set before you see the data, like a fixed recipe.
Precisely. LSH comes with some nice theoretical guarantees about search quality, which is good.
But there's a catch.
Well, yeah. To get really good accuracy, you often need lots of different hash functions, lots of hash tables. And that can mean using a lot of memory and taking longer to search.
Okay.
Though newer techniques, like dynamic collision counting, try to be smarter about managing that.
Right. So theoretical guarantees are nice, but maybe at a practical cost. What about the other one? Learning to hash. L2H. Sounds more tailored.
You got it. Learning to hash methods, they learn the hash functions from the data itself.
Data dependent.
Right. This often leads to more efficient codes because they're specifically designed for the patterns in your data.
Makes sense.
But that efficiency can sometimes come at the expense of those strong theoretical guarantees LSH offers. The main goal is still preserving similarity, though.
Making sure close things stay close, even with the short codes.
Exactly. And there are different ways L2H methods learn. The study mentions pairwise, multi-wise, similarity preserving, quantization.
A whole toolbox.
It is. Quantization-based methods, especially product quantization,
Yeah.
PQ, and its optimized version OPQ are really popular.
PQ and OPQ, how do they work, roughly?
PQ basically breaks down the complex data point into smaller parts, finds the best simple code for each part, and sticks them together. OPQ adds a step to align those parts better first.
Okay, like describing a complex scene by its main colors and shapes separately.
Sort of, yeah. Deep hashing using neural networks is also a thing, but the study mostly focused on unsupervised methods.
Gotcha. So hashing uses shortcodes. What about the second category, partition-based methods?
Partition-based methods take a different approach. They divide the whole data space into multiple distinct regions, like drawing boundaries, no overlap.
Okay.
When you search, you figure out which region your query falls into, and then you only search that region, and maybe its immediate neighbors.
Like organizing a giant library into sections sci-fi, history, etc., so you only search the relevant aisles.
Exactly like that. And tree structures are really common for doing this dividing. KD trees, vantage point trees.
Trees, okay.
Algorithms like Annoy and Flan, that's fast library, for approximate nearest neighbors, fall into this category. They build these trees by repeatedly splitting the data.
Got it. Divide and conquer, basically. Narrow down the search space. And the final category, graph-based methods. This sounds cool.
Yeah, they are pretty neat. Graph-based methods build a network. Each data point is a node.
Like dots on a map.
Exactly. And the connections, the edges between nodes, represent some kind of neighbor relationship. If 2 points are connected, they're likely similar.
Okay.
So the search involves navigating this web of connections. You start somewhere and follow the edges to find the neighbors.
It's exploring a social network?
Kinda, yeah. You iteratively explore neighbors, trying to get closer to the query's true nearest neighbors. K's nearest neighbor graphs, KNN graphs, and navigable small world graphs, or SW graphs.
SW graphs.
Yeah, and its fancy version, HNSW, hierarchical navigable small world, are key examples. They focus on building graphs you can search really efficiently.
Okay, hashing, partitioning, graphs, lots of different ideas. Now, you mentioned the study really tried hard to make the comparison fair. How'd they manage that?
Super important point. They took several steps. First, they compared the core algorithms, stripping away implementation-specific tricks that might favor one over another.
Right, focus on the algorithm, not the tuning.
Exactly. Second, as we said, they used a wide range of metrics: speed, quality, memory, the whole picture.
Not just one number.
No. And they controlled for hardware differences by disabling things like multi-threading or special CPU instructions in the code they tested.
So it's about the algorithm's logic, not just raw processor power.
Precisely. And finally, they used exact KNN search results as the ground truth, the gold standard to measure everyone against.
Makes sense. So after all this careful testing, what were the big takeaways? Which algorithms came out on top?
Okay, the results offer some really valuable guidance. For the best overall search performance, thinking about robustness, quality, speed, scalability, assuming you have enough resources,
Yeah.
diversified proximity graph, DPG, and hierarchical navigable small world, HNSW, were the top choices.
DPG and HNSW. DPG is the new one, right? Introduced in this study.
That's right. It builds on a KNN graph, but is smarter about picking neighbors, makes them more diverse. And it adds reverse links.
Reverse links. Why?
To improve connectivity, make it easier to find neighbors, especially on what the study called hard data sets.
Hard data sets, like...
Things like Noose, GIST, GLOVE, RAND data,
Right.
with complex structures that make search tricky. DPG generally improved on K-graph, another graph method.
Okay. But you said overall. Was there a caveat?
Well, they noted that on data with really distinct clusters, DPG and K-graph might initially rank a bit lower than some partitioning methods, but overall, very strong.
Interesting. And HNS-W. That one's pretty well known.
Yeah, HNS-W also performed exceptionally well. It uses this cool multi-layer structure and a clever way of selecting neighbors that makes it really efficient and robust.
Okay, so DPG and HNS-W are the heavyweights if you've got the compute power. What if resources are tighter? Or you need a good balance?
Then the study recommends Annoy. It's highlighted as an excellent alternative.
Annoy. Right.
It strikes a really good balance between search performance, how long it takes to build the index initially, and just general robustness. Maybe not the absolute fastest everywhere, but a solid all-rounder.
And didn't you say Spotify uses Annoy? That's a pretty good real-world test.
It is indeed. Now, if the time it takes to build the index is your biggest bottleneck.
Yeah, like if data changes really fast.
Exactly. Then Falcon is a good option. It builds its index quickly and still gives good search performance. It's also particularly good for range searches finding neighbors within a certain distance.
Okay, fast build times. Falcon. What about truly massive scale? Billions of points, limited memory.
The really big stuff. For those ultra-large-scale scenarios with tight budgets, optimal product quantization, OPQ, and SRS are strong contenders.
OPQ and SRS.
Very memory-efficient, fast index construction. SRS is interesting because it actually has theoretical guarantees on search quality, and it handles data updates easily.
But, is there a but?
Yeah, this study did find SRS was generally slower in terms of search speed compared to some other top methods.
So a trade-off there. Guarantees and updates versus raw speed.
Pretty much. And just to reiterate, the graph methods DPG, HNS-W, K-graph, they generally outperformed rank cover tree, which is another graph-like method they tested.
Okay, got it. This study also dug into why these top performers work so well, didn't it? Like the space partitioning ones Annoy, Flan, OPQ.
Yeah, the analysis suggests their effectiveness comes down to achieving a really fine-grained partitioning of the data space, almost like running k-means clustering with a huge number of clusters, ideally related to the number of data points you have.
But doing k-means with that many clusters directly would be crazy slow, right?
Totally prohibitive, yeah. So these algorithms achieve it indirectly. OPQ partitions into subspaces. Flan and Annoy use their recursive tree structures.
Clever workarounds. Did they test this idea?
They did. They compared OPQ, different Flan setups using hierarchical k-means, and direct k-means on an audio dataset. The results hinted that hierarchical k-means is a promising direction.
And Annoy uses multiple trees, right? Did they try that with Flan?
They did try multiple Flan HKM trees, but it wasn't as effective as with Annoy. The thinking is maybe the Flan trees weren't different enough from each other, less diverse.
So the way Annoy builds its multiple trees seems key. Okay, what about the graph methods? Why are K-graph, DPG, and HNS-W so good?
Two main reasons seem likely based on the study. First, the true nearest neighbors of a query tend to be really closely connected within the graph they build, like short paths between them.
Okay.
Second, most points in the data set are usually well connected to at least one of the query's true neighbors. This just makes it much more likely that the search algorithm, as it navigates the graph, will actually find them.
It increases the odds of stumbling onto the right path.
Exactly. But as we mentioned, K-graph sometimes struggled on datasets with very separate clusters like Ute and Gauss.
Right, the disconnected graph problem.
Yeah. If your search starts in the wrong cluster, you might never reach the true neighbors. That's where DPG's diversification and reverse edges really help they build bridges between those clusters. HNS-W's neighbor selection also promotes this kind of connectivity.
And they actually measured the path lengths, right? The number of hops.
They did. They looked at the minimum hops needed to get from any point to one of the query's true neighbors. On Ute, K-graph had a lot of points that were effectively isolated, needing too many hops or just unreachable.
But DPG and HNS-W?
Far fewer isolated points, much shorter paths on average. It directly explains why they performed better on those trickier data sets.
So ultimately, it's about building a graph that not only connects similar points, but also makes it easy to navigate between potentially distant but still relevant parts of the data.
Precisely. It's about connectivity and efficient traversal.
Okay, wow. We've covered a huge amount today. Started with the challenge, finding similar stuff fast in big, complex data sets.
Introduced ANNS as the practical solution.
Then dove deep into the three main approaches: hashing, partitioning, and graph base.
We looked at the study's rigorous comparison.
And explored the key findings. Recommendations like DPG and HNS-W for top performance, Annoy for balance, Falcon for build speed, OPQ-SRS for massive scale.
And dug into why they work, the fine-grained partitioning, the well-connected graphs.
So to recap, ANNS is vital for so many modern apps.
Absolutely. And this study gives us a much clearer map of the landscape showing the trade-offs. The best choice really depends on your specific needs and resources.
Okay, so here's a thought to really chew on. Given all this progress in these practical ANNS algorithms, are we getting close to a point where we can reliably find approximate neighbors in high dimensions with, like, near linear index size and sublinear query time for most real-world data, even without perfect theory for every method? What are the big remaining questions, the obstacles to really nailing this for all the weird complexities of real-world data?
That's a great question to ponder. We've made huge strides empirically, but those subtle data characteristics, the quest for even more efficiency, maybe unifying theory and practice more, there's definitely still work to do. It's a fascinating field.
It really is. And for those of you listening, grappling with your own data similarity challenges, hopefully this gives you some pointers. Think about these categories: hashing, partitioning, graphs.
And check out the study's code. The researchers made it public on GitHub links in the show notes. You can actually try some of these open source implementations yourself.
Definitely. Experiment, see what works for you. And we'd love to hear your experiences or any questions this deep dive sparked. Let us know.